and then I'll show you the different approach of problem. So it's better not to solve the problem just in one way. Rather, we can incorporate 3, 4, or 5 ways of problem solving and to understand the underlying concept in that. We have 5 persons whose locations are already fixed, so persons can't interchange among each other. If each of them is given a hat of one of the 3 colors, red, blue, or green, then the number of ways, let's say the first one is given red hat, second one is green, third one is, let's say, again red, if fourth one is I'm giving blue, and fifth one is again red. So this is not a valid configuration. Why? Because here 2 red is consecutive, so we can't use 3 hats of the same color. Why? Because if I place, let's say, one hat even green over here, so now next position where I can keep green is over here, third position I don't have a choice other than to keep green over here, but in that case this will be consecutive. So the takeaway is we can't use hat of 3 colors, so maximum number of hats that I can use is 2. Okay, now with this I can select the hats that can be kept on these 2 positions, A and B. So let's say we have hat color will be either red, red, green, green, or blue, because one hat must be alone, other 2 must be in pair. If it is not so, all the 3 hat cannot be there because number of hat is 5, because number of hat is 5, and moreover you can't use 3 hat. So for these 2 positions, let's say the hat which is coming in single alone is blue hat, it's blue one. Let's say the hat which is coming alone is blue one. So now with blue we can have any combination, let's say blue and red. So now I am left with RGG. Right? Now in how many ways RGG can arrange? At this location C, R cannot come here because it will be consecutive. So we have G, R, G. That's the only possibilities corresponding to BR. So one is alone. I'll have 2 possibilities. Okay, it's either GRG with B and R, or with RB we have again GRG. So I hope it's clear. So now given A and B fixed, we have 2 possibilities, and this itself can go into 2 possibilities. Out of 3 colors, I can select 2 colors to be given to position A and B, out of which one is alone. And now among those 2 colors, their position can be either BR or RB. So color 1, color 2, or color 2, color 1. So that will be given 2 choices. And now A and B were not special, so I could have selected BC or CD or DE or EA. So we have 5 choice, so into 5. So we have 5 choice into 5, and that gives 3 into 10, so 30 as the answer. There is another way of solving this question. Now again what we do, we have 5 persons, 1, 2, 3, 4, 5. Let's first select a person. Let's say first I select person A. So since person A has fixed location, so out of 5 persons, I'll select 1 person, and then let's give him the lone color. Let's say I give him blue color. Okay, so I could have given him any color, either blue, green, or red. So we have 3 choice of them. Now once I'm given him any color, let's say A I have selected and I have given blue color to him. So now I'm left with RRGG. So how many ways are there to put R and G? I can put R, G, R, G, or G, R, G, R. So we have just 2 ways corresponding to red. Okay, this automatically counts if person B is selected in 5C1, because here is person selected and here is color selected for the lone color, alone color. Okay, so if I select a person A and I select the lone color as B, corresponding to this we'll have 2 cases. Similarly, I could have selected A, B, C, D, so 5 possibilities per person, and for every possibility we could have selected any color. This also gives the same result as 30. Let's come to the third solution. Now with basic principle of counting. Let's say person A is given one color, red. So how many choices are there for person A to get a color? 3 choices. What about person B? We will have definitely 2 choices, because if I have used red, the available option is B and G. Now if I have used, let's say, B, now available option is back to red and green. Okay, so we have 2 choice. For person D we have 2 choice. What about person A? Is it having 2 choice? The answer is no. Why? Because that depends what color is left. Let's say I started with red color, blue color, then green color, and then blue color, and then red color. So for person E, if out of two choice. If red comes into picture, then definitely this is not a valid arrangement. So for person E, we can have only two possibilities. Either person E gets the same color as person A, or he gets different color as person A. Right? So either person E will get a red color in this case, or he will not get red color. These are the only possibilities. So either person gets red color, person E, or not red. Now it's very interesting to note that what happens. Let's draw a diagram. It's very interesting to note. Let's see what happens when person gets both of this situation. Let's analyze both of this situation in a pictorial way. So A, B, C, D. Let's say I started with red, and then blue, then green, then blue, and red. In that situation, I start with red, green, blue, red, and green. Okay, so these are only two possibilities when we are counting 3 into 2 into 2 into 2. Right? So in total, we have 3 into 2 into 2 into 2 into 2. Right? So this cases, which is 4, 8. And how many cases we are getting? 3 into 2 cup of 4. So 48. So in 48 cases, we have two possibilities. There will be some cases where the person E is getting same color as A, or some cases when person is not getting the same color. Now, if person is not getting the same color, this is already a valid arrangement, right? So this is the valid arrangement that we want for 5 persons. So answer will definitely be less than 48. That we are quite sure about. But what is the essence of this second arrangement? Now you know, since person E and A in this case have got the same color, okay? So basically I can merge them. What I can tell is this system behaves just like a locked system. Locked system in a sense. Now fundamentally this question boils down to as if there is just one object, one person, E and A together, which is getting just a single color, red, and other person is having different color. So B, G, and B. So instead of, because every time when these two persons will get the same color, I can assume like there is no difference in their, like color arrangement. So I can assume the question reduces to just asking how many ways are there to arrange the 4 person with the same conditions given in the problem. So this is just arrangement of 4. So let's call it this is n of 4. Then this represents number of arrangement of 5. Why it is arrangement of 4? Let's say if I have to arrange now 4 person, which has to be given different color. So I'll give red, blue, green, blue. So now the person E is acting like a dummy because he's also getting red color. So I'm telling you whatever is happening to person A is happening to person E. Okay, so E is not now an independent, it's basically dependent on it. So in that sense, it just counts number of ways of having 4 person on the table, and accordingly hats is being distributed. And that's very interesting case, because whatever wrong answer that we are getting is also correct answer for another simplified problem, right? So n4 plus n5 is going to give me 48. Now similarly, I can repeat the same process for n4. So let's say we have 4 objects or 4 persons. Let's say we have 4 persons. So now if you blindly count 3 possibilities, 2, 2 into 2. So it will be 3 into 2 cube, which is 24. So this 24 will again include n4, all the possibilities when the hats between A and D is different, or n3, and that will give me 24. So we have one equation, n4 plus n5 equals 48. We have other equation, n4 plus n3 equals 24. Even we can come to the next equations. What about if you have 3 persons? That's quite simple. In fact, we can count it easily also, or you can do in this way as well. So 3 possibilities, 2 possibilities, 2 possibilities. So we have 12. 12 contains n3 plus n2. So n3 plus n2 equals 2. So it's kind of recursion that I have got. And you can clearly see this recursion means number of ways in which n person is there, plus number of ways in which n plus 1 person is there, is basically 3 into 2 cup over n. Right? Okay, so this is a general recursion that I am getting. The beauty of this recursion is this 3 is because of 3 colors, right? We could have maybe p different colors, and it will be p into p minus 1 to the power n different person. Now it all boils down to finding the value of n2, and n2 is quite easy because once I know n2 I can find n3. From n3 I'll get n4, from n4 n1. In fact, you can solve this recursion also very easily. It will be just 2 raised to the power n plus minus 1 depending upon odd or even. So it gives a feel of GP, right? 3 into 2 to the power 4, 3 into 2 cube, 3 into 2 square, so on and so forth. So for 2 persons, let's say if you have A and B. Now if I give given green hat, so person B can have anything apart from green. So red, so either it will be GR or RG or red or blue. Okay, so for 2 persons it's quite easy to count because out of 3 colors you can give any one color. So we have 3 choice over here, and for B we have 2 choice. So whatever I have given that I can give. So total we have 6 choices. So we know n2 equals 6. Now with this recursion I can easily find n3. If this is 6, n3 is going to be 6. If n3 is 6, n4 is 18. And if n4 is 18, that's n5 is going to be 30. I hope you really enjoyed the problem, and this was a general way of attacking the problem. I'll not stop here, and as a final solution I'll give you a hint and a basis for inclusion exclusion principle, because some of you might feel like, can you solve this problem using inclusion exclusion? Since the problem can be easily solved using case making in 30 to 40 seconds. Gradually, as my method is increasing, the length of the solution is also increasing. The point is just to give you exposure to different varieties and ideas of problem solving. Okay. So let's try what exactly we want in the question. We don't want A and B to be together. So we don't want A and B together. Similarly, we don't want B and C to be together. We don't want C and D to be together. We don't want D and E to be together. And we don't want, I'll pick up one more color, E and A to be together. Now this beautiful diagram itself shows like what is the definition of set that we want. Right? We don't want A and B to be together means having same color. Right? So we should not have RR here or RB here. So in none of the pair, whether it's AB, BC, CD, D, A, same color should appear. So of course, we can think in this way. Let's say if there is no restrictions of color here. So if A is having all the 3 choices independently, B is having 3 choices, right? Similarly, C is having 3 choice, D is having 3 choice of color, E is having 3 choice. So in total, we have 3 power 5 choice. Now in this 3 power 5 choice, there are choices where all of them is having same color, which is red. Of course, all of them having blue, green, or there are choices. When I get 2 is red, rest is blue, green, blue. Okay, it will also be like exactly 4 of them is red, next is blue, or it can be red, red, blue, red, red, and so on and so forth, or red, blue, red. So there are so many varieties which is included. So all this summation, number of cases and plus many more will be equated to 3 to the power 5. So what we want is not this case, not this case, okay, not this case, not this case, and what about this case? Of course it's not possible because you have R and R consecutive. So which kind of case we want? We want case when one red, we want blue, green, blue, and green. These are valid case. So out of 3 power 5, I have to take away all the invalid case. So how will you define the set? Okay, so here I define, let's say if I define S of A as a set of all possibilities when A and B is having same color. So in that sense, what I have defined set S of P as all possibilities when P and Q, when person P and Q have same color. Okay, so if this is our definition of set, because basically I want to target, I don't want A and B to having same color, or B or C, two consecutive person. So SP I'm defining, okay, the set of all possibilities or the count of all color coding such that the two consecutive person P and Q, P and next person to B should have same color. So SA means A and B should be having same color. What about SB? According to this definition, B and C is having same color. What about SC? C and A is having same color. SD represents D and A is having same color, and SC represents E and A is having same color. Right? Okay. So now, out of total possibilities 3 to the power of 5, I don't want either of them. So I don't want either AB or BC or CD or DE or EA. So this entire 5 different colored set I don't want. So clearly I have to use inclusion exclusion principles. So minus, I don't want SA, union SB, union SC, union SD, union SE. And you know, from the generalized principle of inclusion exclusion, this will be some of elements in A. So mod X represents cardinality of set X, or number of elements in set X. So basically we want out of this, I need to subtract total number of out of total 3 to the power 5, I want to subtract A union B union C union D union A. So SA plus SB till SC minus sum taken two at a time, union B minus A union C, and so on and so forth. And then we'll have plus sum taken three at a time, union B union C, and so on and so forth, minus sum taken 4 at a time, A union B union C union D, and so on and so forth, plus sum taken 5 at a time, A union B union C union D union D. Okay, so now I'll explain some of the terms and what does it mean. So what is, let's count. So we have to count all of them, right? Of course it feels horrific, or you know, like kind of disastrous to calculate all of them, but you can see like there is a rhythm in their calculations. Most of them will be equal. So what is SA? SA means number of all possibilities when A and B is having same color. Sorry. So what is SA? Number of all possibilities when A and B is having same color. Now if A and B is having same color, how many choices this entire system will have? Of course, it will have 3 choices. How many choices C is having? 3 independent choice. D is having 3 choice. E is having 3 choice. So total, if A and B are having same color, we have 3 to the power 4. We don't care about whether CD is having the color which A and B is having, because every case is counted in 3 power 5, and that's the beauty of principle of inclusion exclusion. We don't need to put brain now. So SA is nothing but 3 power 4. Similarly, SB is 3 power 4 until SE is 3 power 4. So we have 5 C1, because I can select any pair in 5 ways, into 3 power 4. Let's come to the second summand. So in the second object, you can clearly see we have 2 varieties of intersection. So we have one variety where number of elements in X intersection B, and we have other varieties when they are not consecutive. Let's say A intersection C or A intersection B, kind of this. Okay. So what is the significance of number of elements? How to count in A intersection B? So first understand what is A intersection B. A intersection B means we want number of cases where AB, A means AB and B means BC should have the same hat, right? So they have the hat of same color. It means this entire system should have hat of same color. So in how many ways they will have the hat of same color? Either it will be red, blue or green. So 3 ways for the remaining 3 ways and 3 ways. So total we have 3 cube ways. So this 3 cube ways will come for either ABC or BCD or CD or D. So we have 5 possibilities over here, right? But since out of 5 we are taking 2 set together, so 5C2, it means 10 ways. It means there will be 10 terms over here. So 5 terms I have already accounted for. What about the remaining 5 terms? So terms like, let's say A intersection C, which is not consecutive. So if it is A intersection C, let's say I can draw the diagram A, B, C, D, E. And now I want AB and CD, because C means C and its next number, to have same color hat. Okay, fine. So basically now I have to group into 2, 2 and 1. Okay, so of course this guy will be left. So here we'll have again 3 possibilities for color, the red, D and C will have again the same color, means A, B and C, D should have same color. Okay, so this guy may be red. And how many possibilities are there? Still 3, and we have 3. Okay, so A and C means A and B is having same color and C and D is having same color. So maybe they will have a red color, red. This is also valid. Or maybe this same color is different. So it's red and blue. This is also valid, because this till now we have not subtracted. So how many possibilities? We have 3 into 3 into 3, 3 cube. And how many cases will be there? Again 5 cases, because the alone guys can be either A, B, C, D. So here still we have 3 cube into 5 cases. Let's say as the next one, S of A intersection B intersection C. So if we have again A, B, C, D, E. Now we want AB to have same color, BC to have same color, CD to have same color. Okay, A intersection B intersection C intersection D, and D to have same color. So if I want all of them is having same color, so the color, let's say, is red, so B has to be red, C has to be red, D has to be red. So how many possibilities will be there? So for 3 of them, okay, so now let's count for 3 of them. So let's say S of A intersection B intersection C when they are consecutive, or when they are not consecutive, let's say A, B and D is there. Okay, or A, C and E is there. So let's see what happens. So when A intersection B intersection C means AB is together, BC together and CD together. So of course they will have same color. So 3 possibilities, and we have 3 possibilities over here. E is the lone guy, so we have 3 into 3, and for E either it can be A, B, C, D alone, so into 5. So that gives you 45 possibilities. Now what if I have A, B, D? A, B, C, D, E. A, B together, same color. B, C should have same color. And now D should have same color. So it's a grouping of 3 and 2, right? So still we have 3 possibilities for color over here, and 3 possibilities here. So that's 9. But how many ways are there to group into 3 and 2? Clearly out of 5, C2. Okay, so 3 consecutive and then 2 remaining. So there will be 5 ways still. So we have further 45 possibilities. Right? So 45 plus 45, 90. Now what about AC? I have got A, B, C, D, E. So A means AB together. Okay, C means CD together, and E means EA together. So it's basically same thing, right? So that's already counted over here in 5 cases. So ABD or AC will be of same varieties. Okay. So we have 2 varieties when 5 times. So in general, for 3 of them, how many terms will be there? 5C3, which is basically 5 factorial by 3 factorial into 2 factorial. So 4 into 5. So it's 10 terms, where 5 of them will give 45 possibilities and the remaining 5 will give 45 possibilities. Total, we are having 90 possibilities. Okay, so for this case, we are having 90 possibilities for the third case. For the second case, we have already seen we have this many possibilities, which goes to 270. Now let's come to the next case. A intersection B intersection C intersection D. So now when we have A, B, C, D, we want S of A intersection B, C, D. So AB together, BC together, CD together. Okay, so we want A intersection B intersection C intersection D. So 4 at a time. So we want AB, BC, CD, and D together. Okay, so for them to be together, now it has only how many choice? 3 choice. But how many terms are there? Out of 5, I can select 4 of them in 5C4, which is 5 ways. So total possibilities, there are 5 terms, and each is contributing in 3 possibilities of count. So we have 5 into 3, which goes to 15. And last, I'm left with ABCD. So S of A intersection B, C, D. So plus, now what about when all 5 are there? So of course there is only one, B, C, D. It's a locked choice. So we want AB, BC, CD, D, and E to have same color. So the only possibilities of color is either red or all green or all blue. So from here, if we calculate, the value that we are getting is total was 243 minus 405, which is our first calculation, 5 into 31. Second is 270, so that will become plus 270. The reason is becoming plus is this quantity we have calculated, so I have to subtract from this. Okay, so 3 ka power 5 minus this one, plus 270. Next is minus 90, and plus 15 minus 3. And if we calculate this, we get 30 as the answer. I hope you must have enjoyed the lecture. More enjoying, the point was how we can solve a seemingly easy problem in a very complicated way, or seemingly complicated problem in an easy way. I'll recommend the best way to solve these kind of problems when the number of persons is small is to use case making. Because if JE were to ask, specifically here, if JE question center were targeting the recursive formula, they could have given you a relation between S10 and S9, or maybe S10 and S8, which I've derived with method 2. Okay, if they wanted you to ask the inclusion exclusion, maybe they would have made their options very elegantly. But here the point was how in a basic style the students can solve this question. I'll come with more lectures, and please do subscribe to the channel, as it takes a lot of energy and effort to create this kind of content.